Hey everyone, so I want to continue with one more thing to talk about with energy. Even though it's in the spring energy section, these are just more of conceptual type questions and how energy a lot of times is depicted with these bar graphs. So try working on this. Pause the video, work yourself, and we'll go over in a second. All right. Now, if you look at this scenario, depending on what you wrote up, you can use this graph to get certain characteristics because there's a lot of scenarios that fit with this. So if I look at this, I start with some potential energy and some spring potential energy in the beginning. So I'm going to start with some height at some height with either a stretch spring or a compressed spring. At the end, I have no more energies potentially. I don't have gravitational or spring potential, meaning that I must be landing near the ground and no longer next to a spring. And not only that, I have all my energy in the form of kinetic. So it should still be moving at the end. So the scenario that you wrote should have something about being at some initial height with some compressed spring and then landing on the lower ground with some speed. There are a few scenarios, like you could be talking about an object on an incline that is at the top, pushed up against a spring, and then shot down the incline. Maybe it's something that's shot off of a table, so it's on a table being shot horizontally using a spring, going like that. Um, Anything that follows that would be a satisfactory answer. Now I'm going to give you a bunch of choices, so pause the video, work stuff, and we'll go over in a second. All right. Now, if we look at these choices, we want to kind of keep that in mind. So if I go through these, choice A doesn't make any sense, mainly because of the fact that it doesn't mention anything about there being a spring. So I have spring potential in my graph, don't have it in that scenario, so A is wrong. B does have a spring on a table, but if you notice, it says when it's landing at the same elevation. If that was true, I would have the same potential energy on both sides, which I don't. So, because I have none in the final section, I have to be landing lower, not at the same elevation. So, my final answer is C. It's the only one where the object starts at a height with a compressed spring. Even though it's being shot up, it ends up landing on the ground lower than where it started. So, this has all the things that I need to check off my list. All right. Here's the next one. Pause video, works off. I'll go over in a second. All right. So, first thing that I want to do is I actually want to see which one of these violates the laws of physics. I don't know if any of them will, but just double check because a lot of times when you have these energy questions, that's definitely, they'll try to throw one of those in there that's violating conservation laws. And that's going to be a good way of whittling down your choices. If you only have to pick through three choices instead of four, it's going to make your life a lot easier to not have to worry about everything. So even if you guess, you've increased your chances to 33% chance instead of 25. And if you actually were able to whittle out another choice, then that brings your choices to randomly guessing 50-50. So if I go through here, energy has to be conserved. This goes up three boxes and three boxes, so six altogether on the left, six on the right. That fits. This one ends up having, I believe this is five and three and another three, so that's going to be 11. And then over here I have five and six. Okay, that works. Okay, here's an issue. This has, I think it's, yeah, five on the left, and then four and four on the right. So I have 10 on the left and 8 on the right. C is not one of my choices. I had to disregard C because it violates the laws of physics. Energy is not being conserved there. So now my choices are between A and B. Now, if I look at the scenario, I can actually figure out which one it's got to be. The key phrase that I actually am pulling out here is this one, that the velocity is constant. So I'm looking for one where the graph for kinetic energy is the same on both left and right. Choice A has 3 for kinetic and 3 for kinetic. So this one works. Let's check out B. This one has 5 or so, I don't know, on the left and then 6 on the right. Okay, that violates what this says. Because the velocity is constant, my kinetic energy has to be constant. So B is wrong. Therefore, my final answer has to be A. So what we actually see here, if we look at the other parts of the graph, we see that what this graph is saying is that the person is doing work to lift up the object. And that's what we're seeing here. The person does work, he's applying a force over a distance to lift this box up and give it potential energy. All right, here's the next one. Pause video, work itself, and we'll go over in a second. All right, once again, they give us this diagram, and I need to figure out which one of these best fits the scenario. Now, one of the things that's important to note with all these choices is that each one of them will have uh, a partially correct statement in them. For example, part A says that the basket is moving. Okay, that is true. Part B, or choice B, I should say, says that the system's energy does not change. That actually is also a true statement. I know that the energy doesn't change because it is remaining at the same height. These forces are constant. It doesn't say anything about it being lifted up. In fact, it's moving to the right, so it can't be moving up. Its potential energy isn't increasing. Its velocity is constant, which means its kinetic energy has to be constant. We don't really talk about heat. There's no spring, so all the energy that this object can have is not changing. So that last statement is that last part of the statement is correct. C, the velocity is constant, the height is constant. Those are both true statements. And then part D, it says that the energy does not change. So again, each one of these choices has a correct statement, and this is definitely important for AP1 questions that you want to keep an eye out for choices like this where part of the sentence is correct, but that doesn't mean the choice in itself is correct. In part A, this is wrong because there isn't work being done. In fact, B and C all kind of say the same thing, that work is done. Work isn't done. Remember, work is the change in the energy in the system. If the energy doesn't change, you cannot be doing work. So the answer actually is D. No work is being done, therefore the system energy does not change. Now, one thing that actually is important is part C, because part C does also have a true statement that if the velocity and height were constant and the person was doing work, then that means that the internal energy, the energy being lost to friction, lost to heat, whatever you want to call it, would then have to increase. The problem is just the fact that Tim isn't doing work in this case. Remember, in order to do work, you have to apply a force not perpendicular, parallel in the direction that it moves. The force that the person is applying, Tim, is applying the force upwards. The block is moving rightwards. That is not in the same direction. That is a 90-degree angle, which means no work is being done by Tim. So D is the only one that makes sense. But again, it's important to notice that there are tricks to these questions that you want to keep an eye out for. What is being said to make this question wrong? What is wrong in the sentence? All right, here's the next one. Pause the video, work itself, and we'll go over in a second. Just like last time, we have another of these graphs. I want to see which ones violate laws of physics. A feels like it looks like it's right. If I add up the boxes on the left, it does equal to 1 on the right. C looks right too. If I add left and right, I get the same thing. So my B is the only one that doesn't make sense. I have about, I don't know, 5 boxes here. I have 5 boxes here plus another one. So that violates physics. I have one extra box on the right. So my choices are between A and C. Now, interestingly enough, these are almost flipped over. So here I have two energies on the left and one energy on the right. Here is one energy on the left, two energy on the right. So let's look at what's going on. The main difference here is whether or not this object starts with kinetic energy. That I can actually see is the difference between these two graphs. So, does the object start with kinetic? Well, since this says that the initial velocity is 0, that means that the kinetic energy has to be 0. So A cannot be my answer. It has to be C. Now, just to double check, I notice here that there is some potential energy on the right hand side. So potential energy is related to height. If I have potential on the right, that means I'm ending at a spot that's not ground level. Is that what I see? Yeah, right here it says that the final height position is greater than zero, meaning that it's going to be landing at a spot above the ground. All right, here's the next one. Pause video, work itself, and we'll go in a second. Now you may notice that this looks almost identical to the previous question, and that's because it is fairly close. The only difference is there's one change. In the previous question, 24, it said a frictionless roller coaster. It no longer says that, meaning that this person is experiencing friction as he goes down this roller coaster. So when I have this setup of energy being converted into more energy as he falls, I have to make sure that my graph includes friction. Now, if I try to do that whole like, is conservation energy being violated? Is there an imbalance on left and right? None of these choices would match because all of them have conservation energy working. But because of the fact that this now has friction, I can actually disregard C, which is actually the graph that I had before in the frictionless setup. This is not going to happen anymore. This doesn't include friction, so I need to make sure that my final graph does. So now my choices are between A and B. Once again, it's actually very similar to the previous case of, where's the energy situated, and everything else is the same. So it makes sense that my answer has to actually be B. It's going to look very similar to what I had before, which was over here, but instead of having all of the energy, or maybe I should say all but one of the energy going into kinetic, some of that energy in the kinetic has to be put into internal, to energy loss to heat, to the friction. And once again, it matches this. I start at a height with no velocity. So I start with potential with no kinetic. I fall down. I I'm traveling at a speed and I'm at some height, so I should have some kinetic and potential, but I should have a little bit of energy being lost to the ether. All right. This is the last one. Pause video, work itself. I'm going in a second. All right. So they say here that a roller coaster is starting here, and we want to figure out what location is this graph depicting. Well, if I look at it, it's fairly straightforward. All the energy that I started with on the left gets turned only into kinetic energy on the right. There is no longer a potential energy. So I'm going to look for the part that would have zero potential. Potential is equal to mass times gravity times height. It's related to height. So no potential means no height. The lowest point in this graph is location 4. So this is the location, or these are the 2 points based off of this diagram. We started at this initial location with some potential and kinetic, and by the time we reach point 4, it has only kinetic. So this was just a little bit of practice of how we can actually uh, come up with information from the diagrams and how the diagrams can be used to convey messages about what's going on. Uh, that's pretty much it. If you have any questions, feel free to let me know. Otherwise, good luck. Have a great day.